And this is a classic projectile motion problem. So a ball that is on the ground is kicked and it leaves the ground at 20 meters per second. And that velocity vector is directed at 30 degrees above the ground or above the horizontal. So this is the initial trajectory of the ball. And we want to know how long is it in the air. So we know that the ball will follow. I'll try to trace this, try to sort of mark out this trajectory. That it'll do something like this in the air. And in part A, we want to know how long is it in the air. So how long will it take from the time it leaves the ground until the time it lands over here? Um, so how long is the ball in flight? What's the x displacement of the ball in the air? So we don't care about landing and bouncing and how far will it roll. We're really only concerned with this. How far will it go while it's in the air? Once it contacts the ground, that's over. The x displacement, we'll call that range if you want. What's its range? How far will it go horizontally? And when it does land, what is its velocity? What is the maximum height that it reaches above the ground? That would be at its highest point. So that's y max. And what's the velocity while it is up there? So at that point, when it is at maximum altitude, we want to know what its velocity is. So I think the best way to approach this problem is going to be to do A, B, and C together, and then D and E separately. And the reason why is if you look at what the problem is asking us, A, B, and C requires that we evaluate the motion of the ball from the time it is launched over here on the left to the time it lands over here on the right. So let's see if we can't do those three together. Um, so x velocity and y velocity, x dimension and y dimension. Let's separate these and say x, x and y dimensions, v naught v a t x, v naught v a t y, our 5 variables. Now let's see what givens we can fill in here. So from the time it is launched until the time it lands, the initial x velocity, it's not going to change. So what's going on here is the ball will have an initial x velocity and an initial y velocity. V naught in the y direction and V naught in the x direction. And guess what? It's a right triangle. We have this velocity vector of 20, but we need its x component to find v naught in the x direction and its y component to find the initial velocity in the y direction. So it looks to me like the initial y velocity is opposite and hypotenuse. That's a sine function. This is 20 sine 30. That's 10. So the initial y velocity is upward. Now, I am going to definitely call up my positive direction and down my negative direction. And to the right, positive, and left, negative. That's my coordinate system. In the first projectile problem we looked at in the last video clip, we called down the positive direction. But if you will recall, the only motion vertically was downward. In this case, the ball is going to travel upwards and then downwards. So if anything is going to move upwards and it's a projectile problem, gravity is going to work against that. One of those will need to be positive and one negative. In that case, we'll just make down the negative direction. So the ball begins from rest in the y dimension and moves upwards at 10 meters per second. In the x dimension, that is an adjacent side. That's 20 cosine of 30 degrees for the initial x velocity, and that's about 17.32, we'll call it. Okay, so 17.32 meters per second. All right. Now, just like in our introductory problem, this ball will not speed up in the air. It doesn't have wings or thrusters or rockets. It doesn't have any of that. It's not going to accelerate in the x dimension. And since we are neglecting the effects of the atmosphere, it will not slow down. So its change in velocity in the x direction is 0 meters per second squared. That means we can treat v and v naught as just velocity constant in the x direction. X, we don't know. We're looking for that. So that's what was asked for in part B, the x displacement. T, we don't have enough information in our x dimension to find the time in flight. So let's look at our y dimension. I actually do already know this final velocity, and I'll explain how in just a minute. But the acceleration we know is g, which is downward at 9.8 meters per second squared. And guys, vertically, if the ball starts on the ground and ends on the ground. Now, a lot of students struggle with this concept of keeping these two different. In the x direction, for the x dimension, the ball's movement was it started over here on the left and it went in this direction and it ended over here on the right. In the y dimension, the ball started on the ground, went straight up to some maximum height and straight back down and ends at the same place that it starts. No, physically it's not the same place, but if you think about the y dimension as rungs on a ladder, then this ball climbs a few rungs and then comes back down and lands on the bottom. In the y dimension, it starts on the ground, travels vertically to a maximum height, and then returns to the ground. So the y displacement, which we know is independent of the x displacement, the y displacement is 0 meters. Starts on the ground, ends on the ground. That's what it did in the y direction. Now, if it starts on the ground and it ends on the ground, all right, y equals 0, and there is no atmosphere, and the acceleration is constant, and it is this constant 9.8 meters per second squared, then it will return to the ground with the same velocity it left. That will be coming down at 10 meters per second. Now, if you didn't know that, it doesn't matter. You could still use v squared is v naught squared plus 2ay and solve for that velocity, but it would be incumbent upon you to remember to make it negative, because if you will recall, when you use this equation to solve for that final velocity, you have to take a radical, and you can't get a negative number. So you are responsible for knowing that that is negative. Now, I just showed you that if you pay attention to the patterns, this y equals 0 for a projectile means that the initial and final velocities in the y dimension have the same magnitude, opposite directions. So it goes upwards at 10, it returns at 10. Now we can find time. We've got plenty enough information to find the time using V is V naught plus AT, so T is V minus V naught over A. So T, the final velocity in the y direction was -10. The initial velocity was 10 over the acceleration of -9.8. That's about 2.04 seconds. That actually answers part A because the time is the same for both dimensions. 2.04 seconds is how long this projectile is in flight. So, 2.04 seconds. I will show all of these solutions when we're finished. Okay, so there's my time in flight. So now let's move down and solve for this displacement. So it's in the air for 2.04 seconds. What's the displacement? Well, if you look at the x side, we have constant velocity and we know the time. If the acceleration is 0, then x is v average t, 17.32 meters per second in the x direction for 2.04 seconds. It's about 35.3 meters. So now we know 35.3 meters was the x displacement. Now to get this velocity when the ball lands, and before I do that, guys, I'm going to show you one little shortcut here to finding this range, the x displacement. This would be an equation that's worth committing to memory, but you must know when it is applicable. And this is only when y equals 0. Only under those circumstances, then the range, right, which is the x displacement, is, let's see, v squared sine 2 theta over g, and that's a magnitude only. Now let me show you how this one works. That v is the initial 20 meters per second. And so if you throw this in your calculator, what is 20 squared? It's what? 400 sine of twice the angle. So that angle was 30. Let's put in 60. And magnitude of 9.8. Throw that in your calculator and see if you don't get 35.3. So this equation is useful if you are asked a question on the exam and you want to know only the range and you need to find out what it is quickly and you don't have time to set up the entire thing and solve for all these other variables. This is a good way to get your range rapidly. Perhaps we'll go through the derivation for that at some point, but it's really beyond the scope of this class. At any rate, let's figure out this velocity when the ball lands. So when the ball comes down over here on the right side, when it comes down, it has some final y velocity and some final x velocity, and we're looking for its velocity vector at impact, and we will give it an angle below horizontal. So that final x velocity, since the x velocity did not change, the final x velocity is 17.32. And the final y velocity, we already know, has a magnitude of 10. So Pythagorean's theorem, we'll get this velocity at impact, the magnitude of this velocity at impact. Well, what do you know? Guys, think about this. This looks like about 20 meters per second at about 30 degrees below horizontal. Now, if you look at these conditions, you can come up with that answer very quickly and not even have to work it out. So the velocity when we land is 20 meters per second at 30 degrees below horizontal. But I want you to look at how we know that without working it out, without solving the problem. We already know that solution. Look at the V naught, the X and Y components of that initial velocity are 17.32 and 10. Well, look at V final. Those components are the same. One's coming down, the negative's not used in the trig. So if the components are the same, of course the vectors are the same. So when the ball was kicked, it left the ground at 20 meters per second, 30 degrees above horizontal. And when it lands at 20 meters per second, and it's 30 degrees below horizontal, which is the same angle here. That angle here. Same thing, of course, same components. Of course, you get the same velocity coming down. Now, in the next part of the problem, we are asked to find the maximum height and the ball's velocity when it is at maximum height. And I told you we were going to do this part separate, and the reason why is because it's evaluated only to halfway of its motion. So the ball leaves the ground, and halfway through its trip, that's where we're stopping and we're figuring out what's going on there. Whereas in parts A, B, and C, we were figuring out what was going on all the way over here at the end of this ball's little flight. So to figure out the maximum height, we don't need the X dimension for that at all. We only need the Y. And we know that it leaves the ground vertically at 10 meters per second. We figured that out already. But now, if we're talking about maximum height, forget what's going on in the X direction. In the Y direction, an object has been thrown vertically upwards at 10, and we want to know how high does it go. Its final velocity, in this case, at maximum height in the Y dimension, is 0. Acceleration is negative 9.8. T we don't know, but Y is what we're looking for, that Y max. And I believe we can get that with this equation. V squared is V naught squared plus 2AY. So manipulating and solving for Y, V squared minus V naught squared over 2A. That final velocity was 0. So 0 minus whatever 10 squared is, it's in the ballpark of 100, over 2 times negative 9.8. That's negative 100 over negative 19.6, which is 5 point something. Where did you put my calculator? Okay. There we go. 5.1 meters, and So that is its maximum height reached above ground. And now let's take a look at its velocity when it is at maximum height. The y velocity at maximum height is 0. We just said that to solve for maximum height. So at its maximum height, it has an x velocity component of 17.32 meters per second and a y velocity component of 0. So the x component is all it has. So at its maximum height, its velocity is 17.32 meters per second to the right or in the positive x direction. And that is the solution in its entirety.